I'm Giorgio Metta. I'm from the Italian Institute of Technology, a research institute based in Genoa, Italy. And I work on human robotics. And in particular, I'm the coordinator of the ICAB project. Today, I'm going to speak about the ICAB, Human Robotics Project developed the Italian Institute of Technology. I mentioned the fact that the robot is open source. And this also, from the educational point of view, I think is important because it basically gives immediately everybody the same platform to work with. So you can repeat experiments, and whereby in robotics, most of the time experiments are demonstrated through a standard video. Here, at least with our project, what we tried to do was to have or give the possibility of various researchers to reuse the software and test, benchmark the methods that have been developed by the community. So if there are 3-4 different ways of resolving or solving a certain problem, a unified platform also enables the researchers to test it for different methods, compare performance, and either try to do better or use the best available method given the task at hand. This, I believe, improves quality in the long term, really quality of the research, and also resonates with the way you do research and development in the industry. There is always been paying attention to the final performance, always making sure things work as they're supposed to be. Whereby in research, often you're just happy with a scientific publication, but then you don't go beyond the scientific publication. So whether the system works for real, it's less important, let's say. By the way, the fact it's open source doesn't mean we're not able to, let's say, make money out of it. And so I believe even an open source robotics platform like this one in the long term will make money, especially providing service, or even if the hardware is open source, doesn't mean the hardware is simple to build. And so customizing the hardware, building the hardware more efficiently will possibly be, it may be a business model for a company that is making money out of human robotics. Our website contains all the drawings, so it's not only software, also the mechanical drawings of the robot or the 3D CAD, and the list of parts and the manual are available from the websites, the electronics, the schematics, etc. So hopefully providing a platform for people to develop on. The hardware was only modified by IIT, by my institute, and the reason is that it's a lot more difficult to do accurate mechanical design than software. So most people are actually downloading the software and using it because it's easier. We have a simulator that can be used. So let's say the learning curve to software usage is a couple of days. If you do the same with the mechanics, it takes weeks, months, depending on your skill. On the software side, since we were opposed to provide a common platform, we also wanted to provide a common interface. So give the researchers the ability to use the same set of standard interface and methods to actually talk to the robot. We relied on a middleware that we developed as part of development work that dates back to 2001. So it's a piece of software I started working with on different platforms. It actually started at MIT and evolved over the years to be used on the ICAB. And in fact, when we started the ICAB project, we rewrote the entire code bases from scratch, maintaining the same set of protocols. So the protocols and the philosophy of the interfaces was maintained, although the code itself changed completely. So this middleware provides two basic components. One is inter-process communication, which is the ability to divide a complex problem in robotics in components that can speak to each other, although they run maybe on different machines, although they run on different architectures, although they may run on different operating systems. And it provides the hardware interface. So the robot is a complex beast, let's say, with a lot of sensors, a lot of controllers, settings to be made before you can actually move the robot. All these things are encapsulated in a set of standard interfaces that are very easy to use, or comparatively easy to use. Also, the fact that we were doing something for researchers sort of forced us to exploit the diversity of research styles. So we made our software working on the three main operating systems. So it runs unchanged, or it compiles unchanged on Linux, on Windows, and on Mac. And this, I think, has been nice because it gives the developers the ability to continue using whatever tools they've been using for their research, and just compiling the iCAP software and be able from their code to control the iCAP. So this was the first choice. We also chosen to basically use a project building environment that doesn't force you to use a specific IDE or a specific development tool. That was another, let's say, again, to guarantee that researchers can use whatever they like. And there's also language portability, which means at the end of the day, our software is just a set of libraries, and they can be linked against any possible language. We exploit Swig, another software that actually generates bindings for different languages. And so people can work in C++, in Java, in Perl, Python, whatever. And even MATLAB. You can actually call iCAP code from MATLAB, which is very useful for rapid prototyping. I was mentioning about the iCAP sensors. There's a couple of sensors that are very important. I say tactile, certainly. There's another way to actually measure the interaction with the environment, and this is through force torque sensors. These are mechanical devices that are instrumented using silicon strain gauges. So devices that can actually measure small deformations in the mechanics and translate that into a force measurement. And if the robot is interacting with the environment, there are exchange of forces at all time, and these forces can be measured. And this can enable the robot to actually generate the correct amount of force given the action that has been commanded. So it's not the robot is infinitely rigid, and it's not even that the robot is infinitely soft. So you can really graduate how much force you make. So on the iCAP, we placed force torque sensors in the arms together with the skin, and force torque sensors in the legs. In the legs, in the latest implementation, there are 4, 2 in the upper leg and 2 in the ankle. And the reason is that sensor in the ankle is useful for bipedal locomotion, for balancing, because it measures the interaction with the ground. And the other sensors can measure whatever is happening to the robot, whether the robot is being touched, or whether the robot just is generating a particular movement that reflects on the force measured. I wanted to mention this because these components become the root of low-level controllers of the robot, and in particular, as I say, the ability to grade how much force is generated. And so the next topic I wanted to touch is how to implement this ability to control force on a robot that naturally doesn't have it. So the typical controller in any robot is, or at least a few years ago, was position control, which means you command the robot to go to a certain position. No matter what, the robot tries to go there. And if it cannot actually reach it because there's an obstacle, the robot will try to increase the force or the torque at the motors in order to overcome the obstacle. It is not correct in most situations where the robot has to interact with people. So it's only correct, strictly speaking, if the robot doesn't interact with anything. So as I mentioned, for instance, let's consider the arm. In the arm, the force torque sensor is placed in the upper part of the arm. And so the sensor typically measures both the external forces, so if there's a stimulation from outside, it gets measured, but also the robot dynamics. Trivially, gravity, so if you extend the arm, you have certain weight, and this weight is reflected on the force torque sensor, but also inertia and whatever the nonlinear dynamics of the manipulator is measured or sensed by this sensor. So what we have to do is basically take the difference between the sensor measurements and the dynamics of the robot. So we have to have an understanding of the inertia and of gravity and subtract them so that we can have an actual measurements of external forces, which are the forces we want to compensate, because those are due to an interaction with the environment, while gravity, you cannot work against it. And this is basically what we done. In the equations in this slide, what we basically see is that for building any controller, what we have to do is build an error signal. This error signal is, let's imagine we're speaking about joint torque control, is the difference between the desired torque you want to have at each joint and the actual torque. And with an error signal, then you can create a feedback loop and actually drive the motors, each motor in fact, so to, let's say, minimize this difference. So as I said, the measurements we have though are not at the joint, they are located at the force torque sensor, and they are influenced by the robot's own dynamics. So what we have to do is subtract the robot's own dynamics, but also map these measurements from the force torque sensor to the joints themselves. Luckily, it's not a difficult process, it's just the mathematics is very trivial and actually very standard in robotics. So we take the difference, we map the force torque sensor measurements at that point to where the external forces have been located, and we know where they are because we have the skin. So we know actually where the robot is in contact with the environment. And then once we've done this mapping, we just map to the joints by using another procedure which is very standard in robotics, which is multiplying this quantity by the transposed Jacobian. This means the transposed Jacobian is just a differential representation of the kinematics of the robot. It's the first derivative basically, and can be trivially computed if you know the structure of the robot itself. So if you know the links, size, and basically the parameters of the structure of the robot is easy to make. The result is that we have, in this way, we have an estimate of the joint torques due to the external forces. And then at this point, we can take the difference, as I said, from the desired joint torques and these measurements of the joint torques and build a controller, which can be a standard PID controller, or it can be something more sophisticated like an impedance controller. The implementation of this on the iCab is a bit more complicated because of the different electronics that measures the sensors, and also the fact that having to compute the body dynamics to subtract it from the sensor measurements require an external computer, because the amount of computation that is needed is fairly high. So in this case, we had to add, the software is not as trivial as may have been. So we did experiments to actually validate this. So in the following slide, we have different ways of measuring the joint torques, and we compare all of them just to make sure that our calculations are actually correct, that what we measure is accurate enough to build a reasonable controller. So there's these experiments that are measurements from 4 different joints, which means the shoulder and the elbow of the robot. We didn't consider the hand in this case. And the plots basically show that 3 different ways of measuring these quantities give the same result, and also that the accuracy is fairly high. So at the joints we have a range of, the working range is from, let's say, 0 to 10 Newton meters, and the errors we get are in the range of 0.1 Newton meters. So it's like 1/100. 1% precision, which is accuracy, which is fairly high in this case, given all the, let's say, unknowns we have in the masses and quantities that we use to do the estimates.